Now I'm going to talk to you about something relatively new that I think most of you probably won't have heard much about, which is exocometary science, which I like to think is a new subfield of planetary system science. Okay, this is the button. Okay, so I'm going to keep it like pretty general, and then show at the end how Origin is really going to shine for us in this field. And this is part of a course. This is not a pointer. This is of course part of the water trail section of Origins, and I think it can play a big role. But it's all relatively new. So okay, so why do we care about comets? Comets are the volatile carriers of planetary systems. They carry volatiles as complex as the amino acid glycine, as found in 2 comets in the solar system, but also simple molecules that are the feedstock of prebiotic chemistry on young planets like the Earth may have been. So there is geochemical and dynamical evidence on the Earth, for the Earth, that volatiles like water were delivered late in its accretion, so in its formation, when the system is around tens of million years old, and most of the gas from the young protoplanetary disk, which we heard about from Coco this morning, is already gone. And these volatiles originated from planetesimals that in our solar system today are located in the Kuiper and asteroid belts. Now, why exocometary science when we can just study comets in our own solar system? So solar system comets have the problem that you can only detect them when they come near enough to the Earth at around 1 AU, and all their volatiles sublimate, and you can detect them in the gas. But that means that the comet has been subject to thermal processing and irradiation. Also, let's not forget that comets have been evolving for 4.6 billion years. And what we have is, I mean, I don't know now exactly the number because it's not exactly my field, but we have numbers of tens of comets with a few data points and lots of scatter. As you can see here in a plot of the abundance of different species in comets, there is scatters that is sometimes orders of magnitude, which may indicate that there was an intrinsic scatter in the composition of comets, but may also indicate that different comets have been subject to different histories. So what we would really like to know is what is the composition of exocomets and their dynamics during the epoch of volatile delivery at the end of the terrestrial prime formation era, when the system is tens to hundreds of million years old. But we know that nearby stars have their own belts, which are detected through the dust that they emit in the infrared. If you look, not a pointer, if you look at the SED. And these are the so-called debris disks that we've heard of that were discovered by IRS now 30, 40 years ago. And so these belts are composed of large exocomets, comets like in the solar system, you can imagine, kilometer-sized bodies that collide and grind down to smaller and smaller dust until you get to dust that is small enough, around the micron in size, that it gets ejected from the system by radiation pressure from the central star. Now, don't imagine these systems like our own Kuiper belt, which is not very massive. We can only detect systems that are 10 to 1,000 times more massive than the Kuiper belt. So these systems are very massive, there's lots of objects, and they're very collisionally active. And so basically, by observing this dust, we know that there must be large bodies present to produce this dust, because otherwise this dust will all be gone through the radiation pressure of the central star. So, so the point I want to make here is that these systems evolve collisionally over time, which means they lose mass over time. And if they lose mass over time, it means that we're biased towards observing the youngest systems. So this is the 24 micron excess as a function of age for these belts that are observed around stars of any age throughout the main sequence, and even in the giant branch sometimes. And you can see that the mass goes down over time. And so we're biased towards detecting, most of our detections are in this crucial 10 to 100 million year period which we're most interested in for the volatile delivery problem. Okay, but I've told you that there is dust and we can observe it, and we infer there are large bodies, but what does that really tell us about exocomets and their composition? Well, so far, not much, but in recent years, this has really picked up. But let's first start from the basics. When the protoplanetary disk dissipates around tens of million years of a star's lifetime, you're left with your star and your outer Kuiper belt-like system with exocomets within it, and a planet, a gas giants that have already formed in the gas-rich phase of terrestrial planet formation. And in the center, which I didn't depict here, you've got like terrestrial planet cores that are colliding and forming and growing. And this is the period at which delivery events may take place. And so how do we observe exocomets in this period? So there are several ways that we can probe exocomets, actually. And I divide these in kind of two categories. We can probe exocomets in the inner regions, which are shown by all of the red markers here. So a planet may gravitationally interact with exocomets within the belt and scatter them inwards until they get very close to the star. And if the system is viewed edge-on, so if you're in a favorable viewing point, you will basically see sort of a transit, a spectroscopic transit in a way that will go away with time. So these were called falling evaporating bodies, and were detected in the Beta Pictoris system 30 years ago. And you find them as basically red-shifted or blue-shifted features compared to the stellar velocities, because these are on eccentric orbits. So when they pass in front of the star, they will have a non-zero velocity. And so this is one way. A more recent way to detect these is through broadband transits. So like you detect a planet, you can also detect an exocomet. And an exocomet will have this peculiar, as we like to call it, upside-down shark fin shape in its transit, which is caused basically by the slow egress when the tail is passing in front of the star, basically. And so this is how you probe exocomets in the inner regions. Oh, another point, the exocomets in the inner regions may leave lots of dust in the inner regions, like our zodiacal cloud in the solar system, which is detected around, and it's commonly detected around nearby stars through exozodi. And Kate knows all about that, but I won't go into the details here. So then the other way that we can detect exocomets, that we can probe exocomets, and that I'm most interested in, and that origins can help with, is the detection of exocomets in the outer belt through gas emission lines, gas absorption and emission lines. So once again, if the system is viewed edge-on, you will see a sharp absorption line on top of a broad stellar absorption line, say in the optical or in the UV, and basically that probes the content of the outer disk seen edge-on. But you can also probe the entire disk, the entire population, by just looking at millimeter and far-infrared cold gas emission, in which you will see the typical double-horn Keplerian disk profile. So this is kind of the basic picture of how we probe exocomets throughout the spectrum. And I'm going to focus on this millimeter far-infrared emission that we've been mostly doing at millimeter wavelengths, also a little bit with Herschel, but we're going to really like break through with origins. So ALMA has really pioneered this field and has completely transformed our view from a couple of systems to now the majority of exocometary belts, or debris disks, as you may call them, that have been observed by ALMA have actually been detected in CO. And here are some major examples, like Beta Pictoris, which has been long known. This is a CO image because ALMA can give us high spatial and spectral resolution, as well as high sensitivity. And this other system, HC2197, where I show basically that the dust and the C18O emission are well correlated to one another, which is consistent with the fact that this collisional cascade that is producing the dust is also producing gas. And I will go in a little bit more into that in a second. But actually, for many systems, well, we're already really getting at the sensitivity limit of ALMA, to the point that we have to use spectrospatial filtering techniques like are used for galaxies to really bring out signals to like a 5 or 6 sigma level here for these very well spatially resolved belts in the dust continuum. And I mean, the amount of CO that we're detecting is incredibly low. I mean, we're talking about 10 to the minus 6, 10 to the minus 7 Earth masses of CO. This is very little. I mean, these stars are nearby, so we're talking about stars that are at a few tens of parsecs from Earth. But still, I think this is the lowest amount of CO ever detected outside of our solar system. Great, but okay. This is an observation. This is the FOMO. No, this is not CO. This is dust. This is dust. Yeah, this is dust. That's what I said. That's what I'm saying. I'm saying that the dust is really bright, but the CO is really faint. I mean, this is just like, yeah, no, it's not CO. Yeah. Not 10 to the minus 6 Earth mass of CO. Great. Okay, so there's very little CO. But really, how do we know that this CO or this gas in general is coming from exocomets, right? You may just argue, because I just told you that most of the systems we observe are tens to 100 million years. You may argue that there may be some cases in which a protoplanetary disk is particularly long-lived, and we're just seeing some weirdos. Well, you can actually argue that the CO must be exocometary in origin, because like the dust, it's a matter of timescales. The CO, there's so little of it that it's optically thin, so it's going to be destroyed by the interstellar and stellar UV radiation field in like 100 years or less. And so for you to see it in so many systems, it's got to be continuously replenished. And the only way to do it is from ice release from exocomets. And I'll show you that this is actually, the numbers are actually reasonable. So we think the CO is second generation like the dust. Next. And how do we think this is working? So I told you that there is this collisional cascade in which large bodies grind down to smaller and smaller things that then get ejected by radiation pressure from the central star. And you may imagine that if you have icy bodies, we're talking about belts that are tens of AU from the central star, like our Kuiper belt, you will release also some gas in the process, where I point out CO and CO2, because those are the ones that will produce the CO gas that we see, because CO2 will photodissociate into CO. And so how do we get to the composition of exocomets? So you can run a steady state argument. So we know that these belts will rapidly reach steady state. So what that means is that the mass loss rate from the top will equal to the mass loss rate of the grains that are being lost by radiation pressure, plus the mass that is lost through the gas. And if you assume that all of the ice, as I depicted here, is lost by the time you get to the bottom, which is reasonable, then you can basically relate the mass of CO that you observe to the total mass loss rate, and you can extract the fraction of CO by mass in the exocomets. And what that turns out to be, so if you look, this is a plot of the ice mass fraction of CO plus CO2, if you like, although we don't know if there's any CO2, because we only detect CO, just to stress that. So the CO ice mass fraction in percentage for different exocometary systems, I only show 3 here. This is an old plot that I should update at some point, but I just haven't had time, compared to solar system comets. And yes, this is a log plot, so there are big uncertainties, but so far, I think we can say that we see a similarity in CO content in solar system comets compared with exocomets, or at least it's telling us that our calculation is reasonable. We're getting out reasonable numbers. I mean, this is the first time we can really do this. So the advantage of looking at these exocometary belts is that you can probe the entire reservoir of exocomets. This is something you cannot even do in the solar system. You're only looking at single objects. So this is the power that you can actually really get the average composition of a volatile reservoir in a young planetary system during volatile delivery. So the natural question is, okay, what about other molecular species that are more interesting than CO? So the problem here is that we're in a mostly optically thin environment. And so here I'm showing a plot of the photodissociation timescale in years as a function of distance from the star, though this doesn't matter so much. Just look at basically the molecules are ordered in decreasing order of photodissociation timescale. So the longest lasting molecules will be the ones with the strongest bond, like N2 and CO, which will last very long. But something like water will only, so where CO lasts 100 years, something like water only lasts like a day. So that's a problem, because basically it makes sense that CO is so far the only thing that we've detected. Now, I had this example for millimeter wavelengths, but I guess in the infrared we can probe CO2 and some of the other molecules as well. But basically, if you remove molecules that don't have strong dipole moment, you're left with basically CN and HCN being the only reasonable candidates for detection at millimeter wavelengths. And we're actually after CN being the next promising target and being produced from photodissociation of HCN. So we can use CN to probe the HCN over CO ratio in exocometary ice for the first time, but we haven't done that yet, but we're in the process of doing it. Now, What does that imply? That all the molecules are being destroyed very quickly. What that implies is that the atomic to molecular gas abundance is very high. So the gas is dominated in mass by atoms. And Herschel already detected for like 3 or 4 systems carbon and oxygen. And that was surprising at the time because we still didn't know of all the CO in the systems detected by ALMA. And what would this atomic gas do? So you have a belt, let's say 100 AU, you're releasing gas from your comets, and this molecular gas is being destroyed very quickly, producing atomic gas. And what will happen to the atomic gas? Well, it will accumulate over time, and it will viscously spread. So this is what this plot is showing. This is the number density of gas as a function of radius. And so if you're producing it, say, at 100 AU, so different lines are different timestamps in years. So after 100 years, it will spread out further and further until you produce what looks like basically an accretion disk. At some time, that will depend on the viscosity of the gas, which we obviously do not know. Actually, the atomic gas may build up fast enough if the viscosity is low enough. You will build up enough atomic gas that it may start shielding CO and allowing it to accumulate as well, making it easier to detect. But this is kind of beyond what the point of my talk today. But then what you would expect is that the atomic gas, if you image it, it would look like an accretion disk. But what we're finding so far, so ALMA is able to image neutral carbon at 500 gigahertz. And we've been able to do only a couple of systems because this is very hard to do from the ground at these high frequencies. And what we're finding is that the atomic carbon is actually co-located with the molecular CO. So this may be pointing to low viscosity, or something is preventing the atomic gas from spreading inwards, or the gas production started very recently. All right, so let's discover our origins. So what can we do with origins to study exocomets? So we want to learn about volatile delivery, and the key is water, as we've talked before, and I think it's obvious to everyone that we want to detect water in exocomets. This has not been done so far. We don't have any evidence for the water content of exocomets, if not very indirectly through observation of the oxygen line with Herschel. And then what is the occurrence and time evolution of these exocometary gas, and how do the compositions compare across planetary systems and compare to our own solar system? And then one little thing that I wanted to mention in the end is how do belts really transition from protoplanetary disks, particularly in the gas. So the first and most exciting thing is the detection of water. So I ran a calculation, and I think this is going to be super easy to detect OH from water with origins in exocomets. And let me repeat it again. This would be the first detection of exocometary water ever. So I did a very simple exercise. I take the range of solar system CO2 H2O composition, which has a very broad range, actually. And you produce OH from rapid H2O photodissociation. And then you account for the fact that OH gets destroyed much more quickly than CO. So you will have less OH in the gas than you would, compared to CO, than you would expect from the ice abundance. And you get out some OH line strengths by just taking how much CO you know is there and just using this abundance ratio. And the line strengths are something between 3 by 10 to the minus 20 and 6 by 10 to the minus 18 watts per meter squared for something like beta pic and 19 parsecs. Now, this big range of like almost, well, more than 2 orders of magnitude, this range only comes from the range of abundances that we observe in solar system comets. That's what that range is. I mean, we don't know what exocomets, so this is the power of origins. This is kind of, we're opening up a completely new discovery space. And so, I mean, depending on how much water we find in exocometary gas, we may be able to, if the exocomets are particularly water rich, we could be detecting it in systems up to 200 parsecs. So yeah, we don't know because it would be something completely new, but at the same time, I'm super excited that we will be able to do this. Oh, and yeah, this line goes just above the Herschel Pack sensitivity, but we did not detect water with Herschel in the one system that we've looked at. So that means that that we can rule out the very water richest abundances, basically, for exocomets. Now, another thing we can do is I told you that atomic gas dominates the abundance. So carbon and oxygen are dominant volatile carriers by mass, and we can actually use them to probe, whereas for protoplanetary disks, you need HD to probe the H2 mass. Here it's exocometary gas, so there shouldn't be that much H2, but it should be atoms that carry most of the mass, and we can basically use oxygen and carbon as like the workhorses for detection of new systems. And what these plots show is the oxygen mass and the carbon mass as a function of distance from Earth in parsecs. And basically, this is the red points is our cometary release model applied to hundreds of known debris disk systems. And what we find is that with origins, we can improve from the 3 or 4 Herschel detections to over 100 new detections. And origins being a survey instrument, we can do this for nearby stars, which are all over the sky. And so it's not as expensive as it would be to do otherwise. It's something, for example, that we cannot do by looking at C1 with ALMA, because it would take forever, and it's very expensive to do at 500 gigahertz. So yeah, we can study the occurrence, we can study basically the C2O abundances and how these relate to system properties. We can really start to have a statistically significant large population of systems with exocometary gas that we can study. And we can spatially and spectrally resolve the gas. So this is an example of the O1 line for a system like Beta Pig, but put at 150 parsecs. So in a star-forming region. So we can detect, I mean, this is mind-blowing. We can detect exocometary gas in a system in a star-forming regions where so far we can't even detect the dust. Yeah, so basically this is the oxygen line, a 63 micron, and you can see we can easily spectrally resolve it with the OSS, and whereas we couldn't do such a good job, for example, with the Spica Safari. And not only that, but because I told you most of the stars are at tens of parsecs from Earth, with the spatial resolution of origins, which is 2.4 arcseconds, we can actually resolve the majority of the belts spatially as well, which would be amazing because it will allow us to study the spatial distribution of the gas and study, for example, this accretion scenario that I mentioned earlier, among other things. And so, yeah, the one last thing that I haven't really made a detailed calculation for, but I think it's good to mention, is the transition from protoplanetary disk. Because as I told you, so just to begin with, I show you basically a plot of dust mass versus age, and this is CO intensity versus age, because it's very hard to get a mass for CO, not knowing the excitation. And so this is the transition from protoplanetary disks, so class 2 disks at 1 to 10 million years, to basically exocometary belts or debris disks at tens to hundreds of million years. And you can see that there's a sharp drop in dust mass, as you would expect. And there's potentially, I mean, it's mostly upper limits here, but there's potentially like a slow decline in a declining gas as well. But basically, again, the CO, like Coco said earlier, CO and the dust don't probe most of the mass in a protoplanetary disk. And so by looking at HD, as she mentioned, we can actually focus and study this transition, whether it's really a sharp transition just in the dust. I mean, maybe dust is just growing and forming planets, and that's what is causing this drop, or is it really the dispersal of the disk, including the gas, and so the HD that we would measure, that is causing this drop? And so, yeah, I think that's also an interesting question that we would like to study. So yeah, I mean, I'll leave you with what we can discover with origins, which is basically, I mean, I think the most exciting thing for me is really the detection of water through OH. Now, I have not done the calculation for water itself, but it should be pretty easy to do. I just have to find the time to do it. But OH is really bright, and so we really should be able to use it to detect exocometary water in nearby planetary systems. And we can study basically the occurrence and time evolution of exocometary gas in over 100 systems using very strong and mass-dominating atomic lines in the far infrared. And we could use HD to study not only young protoplanetary disks, but also the transition between these young protoplanetary disks and the older exocometary belts. And yeah, I'll leave you with that. Thank you very much for your attention.